Great. Our next lecture is given by Professor Fakher Assad, and his title from University of Würzburg, and his title is Fermion Monte Carlo for heavy fermions and frustrated spin systems. Please take over.
Thank you. So I'm happy to be here, and I'll give this talk on numerics. And I looked at the program, and I think it was only DMFT, which does this qualify as numerics? I don't really know. I didn't. But so before starting, I don't know. I should be careful with what I say. So before I start, let me give you a bit of background in numerics. I mean, there are so many methods, and you get lost in all these methods. So I decided this morning to sort of organize these methods as a function of a dimension, right? So Rebecca showed the phase diagram of the Kondo lattice model in 1D, and we know that this is correct because we have DMRG. And so as soon as you are willing to say my life will be a one-dimensional life, then you're good. You have DMRG and everything is fine. Then if you go, I mean, there are of course issues with DMRG. It's not perfect, but it's really very good compared to the other things we'll talk about today. Then if you go to D infinity, where you forget about spatial fluctuations, you can exactly map, let's say, a Hubbard model onto a zero-dimensional impurity model, and then you have a lot of very nice impurity solvers based on Monte Carlo, based on NRG, based again on DMRG, etc. So life here is also easy, right? And so, but actually what happens is that in intermediate dimensions, then things are a bit sticky. It's much harder. And there are many methods, and depending on what you want to do, you will have to choose one or download different packages. So if you say that your physics is close to D infinity, then you can go and say I'm going to take cluster methods. That's DCA, CDMFT, or you can get, I suppose, also some some extended DMFT. I guess that's would extended DMFT, I guess, would be a generalization of DMFT, of course, etc. But these are approximate methods, and they're good, but they're approximate, so you don't really, you have to do an approximation. Then you have variational approaches. So if you know the answer, like left-handed, then everything's good. If you don't, then you can use machine learning, etc., and you can go pretty far with this. And then if you want to start from the methods we have in 1D, which are more DMRG-like, 2D DMRG is fine, but you have the problem of entanglement. And so the computer time, the effort you need grows exponentially with one of the dimensions if you do things on the cylinder, etc. You have to also tensor networks, etc., and you have also exact annualization, which is fantastic, but let's assume that if you want to go at E equals 3, then exact annualization will not get you very far. Okay? So what we want to do today is not talk about all this, but talk about another method, which is a method which is actually quantum Monte Carlo. And this method, these methods we're going to talk about really actually come from so let me take a step back. There are again many quantum Monte Carlo methods. There are quantum Monte Carlo for spin systems, right? etc. Stochastic series expansion of van der Sande, etc. And there are quantum Monte Carlo methods for fermions. That's what I will talk about today, right? So fermion quantum Monte Carlo. And all these methods, if you want, they come from, in a certain sense, they come from QCD people. So they come from people who work in 3+1 dimension in gauge theories and have developed fantastic methods to try to solve the QCD problem, which is an extremely hard problem, where you have all the problems with numeric. And so these methods, I do believe it's correct to say they do originate from QCD. And there are many issues, but the key issue which you hear again and again, I think if you open ChatGPT and you say, what's the problem with Monte Carlo, they say there's a sign problem. And there is a problem with the sign problem, but you can go get around it and work with it, and I'll try to tell you what's it about. So we're going to concentrate just on this, and my goal is to make you understand how to program your code in 2 hours. That's very challenging. We'll see. But let me try, and you can ask questions. Of course, the price I have to pay is that the code you will program, knowing all the formulas, will be so inefficient that it won't work. But in principle, you can do it. Right? That's my goal. So please just stay with me, and that should be okay. Okay, so this is my outline. We're going to start with Monte Carlo. And then I have two applications. Let's see how far I can get. So heavy fermions. It turns out that we can do with these Fermion Monte Carlo, we can have fun with some toy models of heavy fermions. or maybe not so toy models. And I'll tell you how this works out. It's very similar to what Rebecca did. But in principle, what we do is we formulate the Kondo lattice model. Now you know it, you're a specialist. The Kondo lattice model in terms of the U1 gauge theory, compact U1 gauge theory, and then we can, basically solve this with Monte Carlo. And I will give you a set of applications for this. I'll give you applications for where you have some what we call dimensional mismatch Kondo systems, where you have chains of magnetic atoms, let's say on a metallic surface. This metallic surface could be a Dirac semi-metal, it could be a metal. And depending upon the surface, then you see Kondo breakdown transitions, which are actually very interesting, I think, and also then other transitions where the composite fermion, so you know now what the composite fermion is, does not break down or does not destroy. So these are a set of methods, these are a set of applications we can do where we don't have a sign problem. So we can do good things, we can really work on big systems, but even then, if you ask me to ask, so I should not be too negative, but the reality is that if you ask me to get critical behavior, right, what is the critical exponent, this is really tough, right? Okay, but we can get there. And then there's another class of systems which we just started on, and this is remarkable, and you say you have a sign problem, right? So that does not mean you cannot do anything. The problem is that everything is going to scale exponentially with system size and inverse temperature, right? So it's pretty bad. But it's not absolute, right? This exponential scaling, there's a factor in front, right? And so if you're clever, well, if you're lucky, then this factor could be small. And so we were lucky for these materials. And for ruthenium trichloride, so we have been able to use this method for a realistic model of ruthenium trichloride and be able to compare this with experiments, and that's amazing that it works. So we can tame, if you want, the sign problem for these models. Where we can, to be very specific, we can go down to 40 Kelvin. Right? So 40 Kelvin is below the energy scale where you would have the Majoranas and these frustrated spin systems. And then if I have time, we are also looking at phonons, a coupling of phonons in frustrated spin systems. So this is my outline, and I'll start, and you please have to interrupt. Okay? Don't leave me alone here. Okay, so let me start with really basics. And what is Monte Carlo? Monte Carlo is a method to do integrations over a space. So omega is a space of anything. It can be Feynman diagrams, it could be configurations of an Eisen model. It could be anything you want. On this space, I need a weight, right? A probability P of x, and then I'd like to calculate the average of this object. I'd like to do this integration. So P of x is a probability. It has to be bigger than 0 and normalizable. Now, assume that you can get a set of configurations x of I that are distributed according to x of P of x. So somehow I can pull out configurations, and they are distributed according to this probability distribution. Let me assume also that these configurations are statistically independent. That's a big assumption, and you have to be very careful about that. Or in other words, that these O of x of I are statistically independent. Then you can approximate this O of P by this sum. Let's say you have drawn n configurations. It's like 1 over n, sum over all the configurations that evaluate the value of O at this configuration x of I. So that gives you an approximation for your O of P. Okay, very good. So now the question is, how is this distributed, right? So this is distributed according to the central limit theorem. So P of x, so what does it mean? How is this distributed? Let's assume that I'm going to repeat this. So I have pulled out n configurations. You do it, you get a number. Somebody else does it, he gets another number. And then you do a histogram. Then you get a distribution. A distribution is a Gaussian. And the Gaussian essentially has a width, and this width is a variance of the observable. So the error, that's what we call it, is the square root of this object. So you see, many things are very important here. First of all, this works only if the variance is defined. Right? That means that you have to have distributions where the variance is defined. That means fat tails are an issue, are a real problem. And the other thing is that irrespective of this statement here is irrespective of the dimension, right? So I can put as many degrees of freedom in my Monte Carlo run. If I have a good sampling strategy, I don't really care about the number of degrees of freedom. That's remarkable, right? So you can really go to big dimensions, right? That's not an issue. Okay, so here is a reference which is very good. for these methods, if you want. That's where I learned them. So how do we generate? The next thing is, how do we generate those T's? How do we generate these configurations, X of I, right? This is, I draw that out of the box for the moment, and we have to understand how to generate it. So here it is. So we have a transition probability matrix. So T from X to Y is a probability of going from X to Y. I'd like to normalize it, right? So if I start at X, I will go anywhere. I will arrive somewhere. And this has to be bigger than 0. Okay, so this matrix which I find, has to have a couple of properties. First of all, ergodicity. That means that if I pick any two X and Y in my space, then I can find an integer S such that if I iterate S time this matrix, I will find a path between X and Y. It has to exist. Otherwise, I will only sample a subspace and I will get maybe a wrong answer. And all of us did that, right? So that's why you have to check your Monte Carlo to ED. The stationarity condition is the general condition which you would need, is that if I am, it's like a time evolution if you want. So I've arrived at the equilibrium distribution P of X, and I try to time evolve it just, by applying X to Y, T of X to Y, then I have to stay there. This is stationarity. And you see that stationarity is important, is necessary, and that you can, out of this stationarity, you can deduce detail balance, but detail balance is sufficient but not necessary. So that's something important to remember, because our codes don't satisfy detail balance, but we get right answers because we have stationarity. Okay, so that's important. And so if you do that, then you can start with any configuration, and then you can apply this, you can ask yourself the question in a time series of T steps, right? What is the probability of obtaining X? So that's what this equation is telling you. And I'm going to take the limit of the time going to infinity. Then essentially the probability of finding this configuration X in this time series is equal to P of X. Okay, so where does the rolling the dice and everything comes in the Monte Carlo? It comes in here. How do I generate T? And this is the way we do it. Well, we need to define some rules. Well, these are, you yourself, you have a configuration space, and you yourself, you will define some rules. How do I move? I flip a spin for an icing, or I do something as you like it. And this T0 of X and Y, maybe you don't want to stay at the same position. Your T0 of X and Y should satisfy ergodicity. Then out of this, you can generate your T, not your T0. This is called a proposal matrix. Your T matrix, you can obtain it by saying, well, I will go from X to Y I propose the move, and I accept it with this probability. This is the Metropolis Hastings probability, okay? And I will reject it if I don't move, right? If I try to do the step, but it's rejected, then it means I stay at this position. So this is the thing you have to sample, and this is the position at which you're going to roll the dice and see, if this is bigger or smaller than 1, etc. And then you will accept it or reject it. There's another important thing, which is here you always have quotients of P of Y, P of X. When you have a distribution, if you can, normalizing a distribution, that means for us you have P of beta H, the trace. That's basically the partition function. The normalization is very, very hard. Here you don't need the normalization. So you always are going to look at quotient between weights, right? So this is what you have to be able to calculate. So the only thing you need to run a Monte Carlo code is to devise this, it can be slow, and to be able to calculate quotients between weights, and then you can apply all these beautiful ideas, and then you will eventually you'll get an answer. Okay, that's Monte Carlo. Is that okay? You always, if I'm going too slow, you should tell me to speed up, right? I don't know you. Okay? It's okay. So let's go. Oops, that's not okay. That's okay. Okay. Good. So how do we apply this for now? Let's go to real many-body physics. Well, what we do with the Monte Carlo is thermodynamics, equilibrium thermodynamics. Doing dynamics is hard, right? Because there's a phase problem, which makes it rather hard. But we can do thermodynamics, and that's what we would like to formulate. And what we will do, so H is a Kondo lattice model, or you name it. And what we will do is we will rewrite this with, I'll tell you exactly how to do it on a basis for an example. So we're going to sum over a set of fields, 5 which are dependent on space and the imaginary time from 0 to beta. And then I have an action for each of these fields. What is important for the code to work is the possibility to calculate, if I give you a field configuration, you have to be able to calculate the action in polynomial time, and you would also like this action to be real so that this will be positive. That will be the sign. Okay, so how do we do this? Let's go through some a simple example. It's actually very general. I can claim that any Hamiltonian with a one-body term, so that's basically C dagger. C dagger is a vector of fermion operators. So that would be C dagger TC. So that's like a one-body operator. And then the two-body operators, I will always write them in terms of perfect squares. And I think that people who do quantum chemistry will realize that this is a very general Hamiltonian. The quantum chemistry problem, if you talk to Shiwei Zhang, for example, the quantum chemistry problem can always be written in terms of sum of perfect squares. Right? So this is rather general. And I will also assume that O is Hermitian. Okay, so how do I go from this Hamiltonian to this action? Well, there are a couple of steps. The first step is that, of course, most probably H0 and this will not commute. Otherwise, there's no, maybe the interest of physics is not so interesting. And so, so we will have to decompose, if you want, the time propagation in terms of small steps. Basically, we isolate those two body terms. And when you do this, you do an error. And this error in this is called the Trotter decomposition. When you do this, you get an error of delta tau. So at every step in these Monte Carlo codes, you really have to be careful, right? So this is very bad. This way of doing it is very bad. And it's very bad because this is a Hermitian operator. This is not a Hermitian operator, right? So it's really fun is that if you take your delta tau too big here, for example, right, then you will see that your Green's function imaginary time, they start oscillating, right? They say, "Ooh, I have a bug." No, you don't have a bug. You just did a wrong. You did a wrong a Trotter decomposition, which breaks the hermiticity of the Hamiltonian. You get complex eigenvalues. Right? So these are things we have to be careful. And so normally you will go and do a symmetric decomposition, things like that. So just be careful. So this is a step where people have thought a lot, the Trotter decomposition. There's a lot of literature on how to do these decomposition, also for real-time evolution. The next step is the Hubbard-Sutanovich transformation. And so this is just completing the square. So that's not very, that's a Gaussian integration. And here you are, right? So if you put everything together, at every n here and at every time, I will do a Hubbard-Sutanovich transformation. And so I will pick up for every n, so all these n's here, for each n and for each imaginary time, I will pick up a field. And so here I have my equation, which I had before. The action is basically this term and the log of the log of the trace. Okay, so this is what we have. Good. So we're pretty far already. We have a configuration space, and we have this object to compute. Okay. So in the next couple of slides, I will show you how to do that, and that's called integrating out the fermions. What we want, maybe most of you know that you can do this. This is just a determinant of a matrix which can be calculated in polynomial time, right, for a given phi, set of phi's. And the way I will do it is through path integrals, because then we will need the path integral with fermion coherent states, because we will need the path integral to understand the formulation of the Kondo lattice. Okay, so before starting, let me do a simple transformation, right? I'll do a variable transformation. This goes to this, and then I've just done nothing essentially. My H0 is given by C dagger T C, and then I define my V of phi of tau as this original O, which times O times my phi, right? So phi times O is basically my V of phi of tau. Okay, so that's what I will do. Good. So a crash course in Korean state path integrals. I mean, many references for this. What we're looking for are to do these integrations over fermions and to do basically fermion path integrals. We're looking for operators or states which are eigenstates of the annihilation operator. And because of the commutation rules or anti-commutation of the C's, then these variables psi are called Grassmann variables. They're not numbers. They anti-commute, right? They're Grassmann numbers. So Grassmann numbers anti-commute with each other, and they anti-commute also with the fermion creation or annihilation operator. Okay? So there are a set of things you can show. If I had a blackboard, we could do that for one mode. It's very, very easy to do. The set of states, your psi, my claim is that my psi looks like this, right? If you just take one mode, just take x equals 1, for example, you try to apply your C on this, you will very quickly see that you get psi times psi. So psi, the number, times the vector psi. You can do for one mode, you can look at overlaps, right? So that's the overlap of two coherent states. The integration comes from the requirement. These rules for integration come from the requirements that if you integrate f of psi plus a, then it has to be equal to f of psi, and then you'll come very quickly to this requirement. There's the resolution of unity, right, which is given by this object, which you can also, again, do rather quickly for one mode. And then the trace here, which looks like this, and importantly, there is a minus psi here telling you that the trace for fermions is an antisymmetric function. That basically this defines the Matsubara frequencies for fermions. So if you do all this, so we have our propagation here. We're going to apply all this machinery to this propagator, to this one-body propagator. And then you will see, well, at each step here, I'm going to put in a resolution of unity. I'm going to do the trace by using this form, etc. And you will get the integration over the Grassmann variables here, and then you get a set of terms. This is essentially comes from the Hamiltonian. So this is the expectation value of the Hamiltonian with respect to psi of tau and psi of tau plus 1. So here, that's why I have the tau and tau plus 1. This one here with the minus comes from the 1, which I put at every step. And this one here comes from the overlaps. Okay, so we have everything which is clear. And we also have this antisymmetric relation, right? That psi of, that this is antisymmetric, okay? Because of the trace. So it's rather technical. I'm sorry, but there's 2 more slides and then we're done. And so how do I continue with this? So this is what I wrote here on the former slide. And of course, you see, because I have a quadratic Hamiltonian, then I can write this as a psi dagger, a matrix M alpha beta and psi beta. So this is a huge matrix because each of the entries of this matrix, if you want, is the dimension, the linear dimension of your system. Let's say I have a 16 by 16 lattice. So this is a 256 times 256 matrix. Okay. So this is pretty big, and so you can read out the components of M by just comparing, right? So this 1 here, I pulled out a minus 1 here. So the minus 1 comes from this comes, if I take this and this gives me the 1. This times this gives me this minus 1 here. Be careful when I go over the boundary, I get a plus 1 here. And what I'm left here is the Hamiltonian, so this gives me here my Hamiltonian. So the last thing you have to know from the Grassmann variable is that we can now integrate them out. And integrate them out is there is again, this is something which is not extremely hard to show, is that if you integrate over the Grassmann variable, you get a det of M. Right? So this is basically now a determinant. So this M matrix here, we get a determinant of M. And here you are. You've been able to get rid of the fermions at the expense of diagonalizing or finding the determinant of a very big matrix. So let me take one more step because this is not the way we do it. That would be horribly expensive, and even if you're not able, it just won't work at all, right? So here's the point. So let me rewrite things in a better way. So this minus 1 plus delta tau t plus v, I can rewrite it as minus the exponentiation of these two things plus a delta tau squared. And this has this object of you propagate delta tau times the kinetic energy, delta tau times the potential energy. This has the name B of phi of n in some seminal papers, and this is exact up to delta tau squared. So the final result we get looks like this, right? So this is this huge matrix, right? Again, each entry is the volume of the system times volume of the system. And then you can use some determinant identities to reduce it, right? To reduce the complexity. So this is the identity you can use, and you can take here, for example, we can do one step together. I'll take this here will be my A, right? This here will be my D. This here will be my B, and this here will be my C, right? We could do it on the blackboard, that would be better. And then if you take this, then you've reduced the det of d is equal to 1. You've reduced this to a smaller size, right? And you can recursively do this, and then what you get at the end of the day is the det of 1 plus b of L of tau up to b of phi, right? So this is now a simple equation, right? I in principle know how to multiply matrices. If I give you the phis, you can multiply all these matrices, add 1, take the determinant, and you have the weight of your configuration, right? That's it. So that's what you need for, that's what you would need for your Monte Carlo. Good. So we know how to do Monte Carlo now. So the Monte Carlo in principle is done. I have this space of variables. I can basically decide to move one phi around, and every time I move it, I calculate the quotient of the new weight to the old weight, and I will accept it or reject it, and that's it. Okay. So now let's move on and see a bit what happens with the sign problem, right? The sign problem is an issue, and why is it an issue? So generically, this determinant or the trace of this is not positive, right? It can be negative. And so there's a lot of literature where ask the questions, under which conditions can you show that this determinant is positive? Now, there are many cases. The easiest possible case is because of some type of Kramer's theorem. So I will assume that for each of these phis, I will assume that there exists an anti-unitary matrix, for example, time reversal symmetry. So anti-unitary matrix would be a unitary matrix times the complex conjugation, right? So U dagger U equals 1, K is the complex conjugation. It has to be for fermions, so T squared scales to, T squared is equal to minus 1. And I will assume that for each of these configurations phi, that T will commute with phi, with T commutes with U. And then we can show that this object here is positive. Now how do you show it? It's actually pretty simple. What you do is you go and look at this determinant, and what you will do is use Kramer's theorem to show that each eigenvalue of this matrix here comes in complex conjugate pairs. So this is it. If I have an eigenvalue of this matrix, right, which is lambda, then lambda bar is also an eigenvalue, right, but with an eigenvector T of nu. And now, importantly, these two, importantly, because T squared is equal to minus 1, these two vectors are different. So you have really two different states for those two complex conjugate eigenvalues. So this is Kramer's theorem, which you use to show the absence of negative sign problem for a big class of problems. There is one caveat in this calculation. You have to be a bit careful. If you don't think about this, you can get carried away and believe that you've solved the sign problem for many problems. When you do the calculation, you have to be sure that T of the vacuum stays the vacuum. If you use particle hole symmetry, this is a bit of an issue. So essentially what this tells you, you need an additional U1 symmetry. I won't go there. So for example, all problems which have time reversal symmetry are solvable problems. Now this is not so, for example, if I give you an arbitrary set of conduction electrons with a Ashba spin-orbit coupling with an attractive interaction, that's already pretty complicated. You can do the symmetry. There will be no problem. So all these attractive, these problems which map onto effectively attractive interactions, they work out very nicely. Okay, question? Yes.
I have one very basic
question. Oh, very, thank you.
At the beginning, you talked about there is a transition matrix, right? Yeah. And we have some time step.
Right.
So we are multiplying these matrices together. But I just want to clarify, so this time step is different from the time step in your imaginary time.
Yeah. So there's a, yeah, of course. Right. So there is a time step in the coherence. Yeah. So what you call this is Monte Carlo time. It's the Monte Carlo time of the Monte Carlo process. So that was the first time. And then there's the imaginary time for the imaginary time problem. Okay, so there are two times. Okay.
And in practice, we need to choose those time steps?
No, normally the time, so the time step for the Monte Carlo is basically discrete, right? You don't really care. You just say, okay, if I have an Ising spin, the time step will be take one step, flip the spin. Take one site, flip the spin. That's it. That will be one unit. For the Monte Carlo, you build in a systematic error, right, by taking this time step delta time. So you have to be careful. I think the rule of thumb is the following: if you're looking at criticality or universality, then you should be careful not to break a symmetry by these delta time. That's not always very trivial. And if you don't break symmetries, then you can choose it pretty large. If you break a symmetry, you have to be very careful. So that's tricky. That you have to be careful. Thank you. Good question. Okay. Good. So this is a case where we have no sign problem. Unfortunately, there are many cases where we do have a sign problem. So this would be a case where the determinant, the log of the determinant gets an imaginary. The argument is non-zero. Right? So no sign problem. We have this computational time. Sorry, I'll go one step back. V to the cube times beta, and then I went too quickly, right? So in the absence of sign problem, this term is equal to 0, and normally this is a method which works in polynomial time. And these are a set of very nice papers which enhance these idea of how to use symmetries if you want to get rid of the sign problem. Okay? So what do we do if you have a sign problem? Well, this becomes now this one way to go around it is to say, well, I'm going to sample something different, right? I can only sample something which is positive, and I'm going to sample an auxiliary partition function based on a different action, which is S bar, where I just bluntly forget about the imaginary part, about this imaginary part. Now, when I do this, I can rewrite everything, and at the end of the day, I can build up the Monte Carlo for this different weight or this different action, and at the end of the day, I see that we'll have to divide by something which looks like this. This is the original partition function. And this is the partition function of a different problem. Now, generically, the partition function of a Hamiltonian, let's assume that I can map this onto an auxiliary Hamiltonian, then the partition function of a Hamiltonian scales as e to the beta times v, right? Beta, the inverse temperature, and v, the volume of the system. So you're going to get two numbers which scales like e to the minus beta v, and then you'll take the quotient, and the odds are that this alpha will not be 0. I mean, you can maybe fine-tune it to a 0, but that will be very, very special. And there are some special cases. But generically, this is not the case. So that's fine, you would say. You would say, well, this is a small number, and then I can do my Monte Carlo and do my Monte Carlo more and more, right? But you should not forget that this sign, I will be dividing by this sign, and that means the fluctuations, the error on this sign, has to be smaller than the value. Otherwise, I'm in trouble, right? Otherwise, I'll divide by 0. If I have a small number, I have a stochastic process, to divide by it, I have to be sure that the error is smaller than the value of the number. But then if you don't forget the central limit theorem, the central limit theorem tells me that the error on the sign is proportional to 1 over my computational time. Right? So 1 over my computational time will have to scale exponentially. Right? That's the problem. So, the computational time will have to scale exponentially. So that's it. Right? So of course, this is not, so you could say this is the end, we won't do this, and for a very long time we've done it. But then you realize when you play around with those path integrals, a path integral is not unique, right? You have many, many path integrals, and you can come up with an idea and say, well, let me optimize over all possible path integrals, right? Such that, that's easier said than done, I don't know how to do that actually. But you can say, let's optimize over path integrals, try to minimize the alpha. And in some cases you can do that, and in some cases you can really get very nice physics, and you can compare experiments even with a sign problem. But this is more like on a case-to-case basis where you have to be lucky. Okay. Good. So, yeah. Alpha is a number. So the point is that this alpha, okay, so I went too quickly. If I have a partition function, right? If I have a partition function, I take the limit beta going to infinity. And it scales as e to the minus the ground state energy density times beta times v. Okay? Now, this is my original partition function. This is an auxiliary partition function, and it will scale as e to the minus e0 tilde times beta times v. And alpha is the difference between the fermionic ground state energy and the energy of this auxiliary Hamiltonian. That's it. So this is what you have to optimize. This alpha. Okay. Good. So this is so now you know how to do Monte Carlo, and you can program it yourself. But we've done it for you. So this is a package we have been playing with all these people, and this is great fun actually. The question you ask yourself is, so you guys can ask yourself these questions also. What is the most general Hamiltonian I can write down so that each model I will ever want to simulate will be able to be, plugged into this form. Right? So my claim is that this is not so far from it. And so we have a one-body term, right, which you can plug in. And we have some symmetries. Symmetries are very important to optimize the thing. So we have these C fermions. These are fermions. They have a position on a lattice. Sigma, we call this a color index, and S, we call this a flavor index. You will notice that all the matrices T, V, I, they have no sigma dependency, which means that our Hamiltonian has an SUN symmetry. Right? So there's an SUN symmetry in the Hamiltonian. Then you will see also that everything is block diagonally in the S, right, etc. So we have the possibility of a single particle term, a two-body term, which is the square of local single particle terms. And also we've been working a lot with Z2 and U1 gauge fields, gauge theories. So we have the possibility of putting an Ising or a scalar variable here, which couples to a one-body term with a given Ising, with a given dynamics, which is given, right. So this would give you the possibility of doing electron phonons, for example, etc. So it's a code which is as usual, we do our best to make it easy to use. It is not so easy to use, I guess. This is programmed in Fortran 2008 because of historical reasons. And, but I convinced all my young collaborators that Fortran is not so bad. If you go and look at, I won't try to do this to you, and I'm not being recorded, but they've accepted. But nevertheless, we have a Python interface, we have a Python envelope, etc., so that you can use this from any of your Python. So if you're interested in this, you can come and visit us in Würzburg. We're going to do, we do every second year, we do an Alp school. You're welcome to come. Würzburg is a very nice town in Germany. It's just 11 hours to fly. There's a direct flight from Houston. Not to Würzburg, to Frankfurt, but then once you're in Frankfurt, once you're in Europe, you're everywhere. It's not like, Europe is small, and Germany is small compared to your distances. And so you can, well, it's not yet announced, but I mean, if you want to join, it will be also hybrid, so you may want to join hybridly if you're interested in using all these things. Okay, so that's it for my Monte Carlo questions. Not so many questions, good. So let me start with heavy fermions, and I can go quickly because I guess you've done a lot of, we heard a lot about introduction to heavy fermions, but a couple of things which will relate to what Rebecca was saying in the morning. So these are some of the people with whom we've worked a lot on these heavy fermions. These are all people who, well, Zihong is now left. He went to Dresden. Bernhard left physics. Manuel is in Munich. Marcin is still in Würzburg. Tarun Grover, you may know him. Matthias Voita is in TU. David Luitz, he's in Bonn. And Lukas Janssen, he's in TU. And some other people like Shaunak Wiswas, who's in a group who's already working with us. I'll tell you more about this. So this is the periodic Anderson model, and it's basically, you've seen this many times. And it's basically the description of two types of orbitals, one extended orbitals and one type of localized orbitals. On these localized orbitals, you have a strong Coulomb repulsion. So as Rebecca did, you can say, well, let's start with the U equals 0 limit. Right? If you take the U equals 0 limit, well, you can diagonalize things and you will get those hybridized bands. Okay? And you will get also something which is important, which is a large Fermi surface, right? If you do the diagonalization of this, Luttinger's theorem will hold. And you will see that the volume enclosed by these hybridized bands, this is this object here, counts the number of conduction electrons plus the number of your d electrons divided by 2. Okay, so that we understand. What is remarkable is that this picture comes over and over again also in the large N. Right? You always see the same picture. The question is why? I mean, this is something which confused me and which we can actually answer with the Monte Carlo, I think. Right? So this is a diagram which comes from Piers. And it turns out, so let me step one step back, is that the heavy fermion phase, the heavy fermion paramagnetic phase, ground state is adiabatically connected to the U equals 0 limit. So if you start here at 0 temperature and you prop up the U, right, then there is a phase which is strongly correlated where the mass of the electrons becomes very large, and which is stable, right, up to a quantum critical point, maybe where some new phases occur. So if you so this picture, right, actually holds up to for the ground state of these heavy fermions. And of course, if you're at strong U, then you will start melting this phase if you want. You will come into a local moment regime, which which is then, of course, different than if you melt. This is the coherence temperature. So essentially, what happens as a function of U, the coherence temperature sort of crashes down, and the mass of the particles gets bigger. Okay, so we don't work with this Anderson model. And we don't work with this Anderson model because it's actually technically easier. It's much easier to do. But from the physics, it's much harder. You have charge fluctuation. If you want to go to the local moment regime, then the Kondo scale crashes down, and you have to cool it. So it's very hard. So for us, it's very nice to be able to work with the Kondo lattice. And as you learned this morning, the Kondo lattice is essentially a canonical, in a perfect world, it's just the same model, but it's a canonical transformation of the Zhu-Schrieffer-Heeger transformation, the canonical transformation of your original model. So of course, this equal is wrong. That's more or less equal to, because there's some approximations. And what you will get is, again, your conduction electrons here, and then this JK term. This JK is proportional to V squared over U. Okay? So one thing you can ask right away is, and this was answered this morning, is what happens to the Luttinger count, right? So in principle, when I go from here to here, this is a canonical transformation. So if the Luttinger volume is here given by a number, then it should be the same as this one here. So it turns out, as Rebecca said this morning, is that you actually generate a new particle, which is a composite fermion. And the way we see this, or you can see this, there are many ways of understanding this composite fermion, is to say, well, let me take the D operator and pass it through this canonical transformation. Right? So I can do that, and what I get is exactly something like the operator which Rebecca showed this morning. This is this composite fermion. Importantly, this composite, because the canonical transformation, this has the same quantum numbers as a fermion. It is just a fermion. So if you go and you see how does this transform under an SU2 transformation, it just transform as a bare fermion. You know, how does it transform as a U1 gauge? It just, you know, it has the charge and the spin 1/2 of the electron. So what is very nice with the Monte Carlo, you can say, well, okay, I can set up my Monte Carlo and I can look at these. Do I see these hybridized bands? Right? So this is a calculation with it's on a 16 by 16 lattice, I think. It's at low temperature, it's at 0 temperature, because we have different ways of doing this. It's a large JK over T equals 2. And what you can look at is the spectral function of the conduction electrons, which is this. So you see again those hybridized bands, and you will see that essentially you lose a lot of weight. So this is at the gamma point. So you have this is a band which has sort of D character or heavy fermion character, which you pick up very badly if you want when you measure the conduction electrons. And then if you decide to measure the correlation function, the spectral function of the composite fermion, right? So this is this fermion here. You can just measure the spectral function of this composite fermion, then you will see that the missing weight, which you have here, it comes up again here in this composite. Okay. Good. So now, how do we get those results, right? And how do we formulate the Monte Carlo for these heavy fermions, for the heavy fermion problems? So essentially, this is works which comes from, I mean, we just follow, the Monte Carlo follows work which comes from Patrick Lee, and there's a very nice paper inside Serre. Right? And so we change a bit the model now, just because to make it more general. So we have our Kondo lattice model here, and then we add a direct Heisenberg exchange between the localized spins. Okay, so why not? And now the question is, how can I write this in terms of my perfect squares? And this is the way we do it. We take an Abrikosov representation of the spins. So that's a spin operator, provided that I impose the constraint, right? The Kondo lattice model lives in a Hilbert space where I just have one electron per F, right? So this constraint has to be imposed. And so if you can rewrite, there's an exact mapping from here to here. So this is the conduction electron. This hybridization here to the squared, this V is basically F dagger C. If you take the trouble to calculate this, then you will get exactly this number here, provided that you impose the constraint here with the U. And then for the Heisenberg part, you have to write it in this way. So this D of B, which is basically the hopping of an F electron from R to R prime. This here will map exactly onto the Heisenberg. So 10 minutes. So with questions? Yes. Yeah. Go ahead, before questions. Good.
Yeah, I'm curious why you're adding the Heisenberg term. Physics should actually emerge from
Yeah, you're right. You're right. We were interested in. You're right. We were interested in in cobalt atoms on a metallic surface, and there it turns out that there is some type of direct exchange on top of the RKKY. That's what the experimentalists tell us. I can't do it. So we decided to put it in. Right? That's all. But in principle, it should come out. In principle, it should come out. This gives you an independent parameter to play. Okay, so this is, okay, so you can ask the question, so we start with a Hilbert space here, right? We start with a Hilbert space here which has no double occupancy, and we're going to work in the Monte Carlo in a Hilbert space which has double occupancy. And so we have to be sure to be able to get rid of it. And this happened actually very, very nicely because the HU is basically, the Hilbert term just basically counts the parity of electrons. There's 1 or 2 electrons, that's all. And so you can see that all these terms here, they don't change the parity of the F site, which means that H and HU, they commute with each other. And so if you do your Monte Carlo, you see that you can predict that the double occupancy will crash down with this law, and in fact it does. So what we do, we place ourselves normally here. We're sort of 3 orders of magnitude below the free electron case, and then we're happy with it. So this is as good as exact, right? So then how do we do our Hubbard-Satonovich? The Hubbard-Satonovich looks like this. I need so I'll do the same Hubbard-Satonovich I taught you about at the beginning. For this, I need a real field, and for this, I need another real field. So for this object, I need a complex field, which I call B of R, which is the norm of B of R and e to the I phi of R. So this, I need a complex field to decompose this object. Then I need a complex bond field to decompose this object here, which I will write like this in a convenient way as the amplitude here, and then the phase will be an integral like a vector potential. Why not, right? And then I need a real field here to decouple my Hubbard term, right? So that I will call A0. And then I can do everything now, do my Grassmann stuff, etc., do my Hubbard-Satonovich, and I will come down, I will obtain an equation here in the limit where U equals infinity, which is actually a U1 gauge theory, right? And what does that mean? So I have these fields here, psi b, right? The psi, the b, etc. This is my hopping for the fermions. This is my hybridization, if you want, between the f's and the c. Don't forget the phi. This is the dynamics of my spin-ons here, and this is the Berry phase, if you want, for my spin-ons, and this is the dynamics of my spin-ons. Okay, so this is my Hamilton. And then what we do with the Monte Carlo, as I already told you, is, well, we can do this integration over the Grassmanns analytically for each configurations of C, B, and A, and we will get the log of this determinant, which I told you about before, and then we're left with the integration over the Z, B's, and A's, and that, for a set of problems which have some symmetries, which I'll talk to you about afterwards, we can do that exactly without any approximation. So we're basically, the way to do the Monte Carlo here, in this case, is to sum over all the fluctuations of the U1 gauge. Okay? So that's the method. So what about the symmetries? So there is global charge, right? So the F are not electrons, right? These F are spin-ons, they carry no charge. The C's, they carry a charge, and there's global U1 symmetry. So if I do this transformation like this in this action, and I care to shift the phi, if you want, is the Hubbard-Satonovich, which coupled to the hybridization. So this object has a charge because it's C dagger F. And so this phi transforms as phi plus alpha. Like this is just a variable transformation when I do an integration over my fields. And then nothing changes. Now, for the F, there is a local U1 transformation invariant because of the double occupancy, right? And essentially, what I'm telling you is that if I do the transformation, F dagger goes to F dagger plus a local gauge transformation, so now this number depends on R and tau, then I can compensate this by just doing a gauge transformation for my fields A0 and A, and also for my phi. Okay? So basically, what I'm telling you is that I can, within this field theory, I can now understand what this composite fermion was. And in principle, the composite fermion, I'm going to look at my equation, my things here, and I'm going to tell you that you can see rather quickly that if you consider an object in your Monte Carlo, which is the composition of your F, that's your spin-on, times this E of I phi. E of I phi is the phase, if you want, of the hybridization. Then this object has the symmetries of an electron, and that's basically the composite fermion. So if you take a simulation, you say, okay, let me calculate the propagator of f of I of tau, f of j of tau, you'll get 0. They won't propagate. If you care to multiply it by this phase factor and do the same calculation, then you will see that this object then becomes a Turner. So that's essentially this f tilde fermion, which we'll go before. I have 5 minutes. Okay, so in 5 minutes, I would like to tell you, there was a question about the large n, right? And so what I'd like to show you is that it's possible to do these simulations from n infinity, that's the saddle point, to n equals 2, and to follow the physics and show that there is no phase transition in some special case. And that gives you the notion that this, mean fields type large n calculations we do for the Kondo, that's actually has a sense, that it's really correct. I think that's not so trivial. So in the Monte Carlo, we can go from SU2 to SUN. The coffee break is come. Yeah, I still 3 minutes before. I can change the symmetry, right? I can go from SU2 to SUN. And the cool thing is that you may think that's very complicated to do. Well, in our Monte Carlo, that means just multiplying this S by N, and you have a new paper. That's something people know how to do, right? So this is, you just multiply by N and you just run the code, right? So this is a parameter in the code, nothing else. And then, of course, when N goes to infinity, you have the saddle point equations, which Rebecca showed this morning, and you get those hybridized bands. Now, this is a work which was done by Marcin Rakowski, and it's basically systematically looking at the half-filled. We can only do half-filled in this case, so it's a Kondo insulator, right? But nevertheless, so this is the Kondo insulator at n equals 1/2, so n equals 2, as a function of j, right? This is the RKKY phase, so this is the pure Kondo, no JH. So this is the RKKY phase. I have an O3 transition to a disordered phase, which is the Kondo insulator heavy fermion phase. It's very interesting to see that these order-disorder transitions survive for larger n's. The RKKY interaction is normally suppressed as a function of n, and what we get, we still get some transition, but these transitions, they actually become first order for those symmetries. I won't go there. But the only thing I'd like to tell you is that these red points here, basically the physics I have here at n equals 8, and we could go on to larger values of 8, is adiabatically linked to this one which I have here, right? So there is no phase transition. I can do my Monte Carlo systematically for, I went too quickly for here, because the chairman's up, so I'm getting nervous. We can only do for even values of n. We can't do for odd values of n, right? So for all the even values of n, we can then go from n equals infinity to get n equals 2 and really be able to claim that large n is okay, right? Which is something which is not trivial to do. Okay, so I'm done. We can classify all these phases with those gauge fields. We don't have to. We can start up with this tomorrow if you want, but very quickly you can say, well, what is a Kondo phase? A Kondo phase is a phase where sort of this B, there's a sort of Higgs mechanism, if you want, for this B condenses, right? But the F doesn't. There's no order, right? So that's a bilinear does not. So that would be a Kondo phase. You could have a spin density wave phase where you have no Kondo and then you have basically this condenses. You have Kondo. Those two things can coexist. There's no symmetry which says that won't, right? So you can have B and the Kondo and this which is the same. You can have these Kondo breakdown phases where nothing condenses, no spin and no B, and then you get the crisis in some cases for the Luttinger volume, right? So then there are very nice ideas of Oshikawa that a way out is to be sure that the gauge field is deconfined. So these are these FL star phases. And you can continue. You can say, well, I can have magnetic order, and I can not have any Kondo, but also have a gauge field which is deconfined that will give you these SDW star phase, etc. So my point here is that on the basis of this U1 formulation of Kondo physics, you have a very clean way of defining the phases, and you have a very clean way of doing Monte Carlo, and you have a clean way of going to large n, right? Good. So tomorrow we will go through this, and just as a teaser, These ideas of cobalt atoms on metallic surfaces. I'll only go through this and this tomorrow if I have time. And these turns out to be remarkable systems. Right? Okay, you want me to shut up? Okay, good. I'll shut up. Okay, good. So come tomorrow.
Thank you for the great talk. Is there any question for the speaker? I think you are first, actually.
Okay. Yeah. Thank you for the very, very clear talk and like very clear explanation of DQMC. I'm just wondering, I mean, in your kind of notation or construction of your like implementation of QMC. So what's the difference between flavor and color?
Yeah.
I know that there is some.
So the flavor, it's your block diagonal. The flavor is like a U1 symmetry. The color is an SUN symmetry, right? So you see that this one, all the T's, if you want, they are diagonal in S, right? That's the color. That's the flavor symmetry, but they have no dependence on sigma.
So in practice, if I want to solve some model, I just need to identify what is my flavor.
Yeah. So you have different ways of doing it. You have to identify that will gain you a lot of CPU time. Right? So that you have to do that, otherwise you just lose.
Okay, thank you.
You mentioned this relationship between symmetry and sign problem.
Yes.
So I think the example you gave was tabular.
Yes, exactly.
So can you use the sign problem to predict what the tabular symmetry or some other symmetry?
It's a very complicated way of predicting time reversal symmetry, I must admit, but it's a good question. I never thought of doing it this way, I must admit. Why would you? No, it's a good question. I'm trying to gain time by joking around, but I'm not finding a good answer to that. You see, the sign problem is dependent on chemistry, on small things, right? So when you're working, you're just playing with things and it works or it doesn't work. So you're never very sure, right? That maybe you haven't found a nice trick to get rid of the sign problem. So it's maybe not a good way to do it. Yeah. She decides. That's a good question. If it's confined or not confined, well, it's a good question. It's very hard to. There are some. I forget the. There are some. In the case of matter, when you have matter, gauge field matter, there is. I forgot the name. A correlator which you can use, which is the Wilson loop square root divide. There's basically. Does somebody know how this is called? It's basically you have your matter, which with a string connects with another string from 2 points, and then you divide by the square root of the Wilson ratio. Now this correlation function has a name, and this will be able to, in principle, tell you if you're confined or deconfined. I'm sorry, I forgot the name. It's just impossible to measure, right? It's just so hard to measure that you only get noise. We try. So at the end of the day, you just look and you look at basically your fluxes, you look at basically your physics, and then you say, well, maybe it's deconfined. But that's the only thing I can tell you. That's the truth. That's the blunt thing we do. Because all these other things which the QCD people tell us you should do, we try to do them, but it's too hard.
Yeah. I found this Fermion representation of spin, and then you said the constraint can be very efficiently.
Efficiently. Efficient.
Efficient.
Yeah.
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 So I found that to be very interesting because here there's reason to consider the fermions to be the ultimate execution.
Right. Right.
So I wonder whether one could also do that for pure spin models.
Yes.
In frustrated cases where there's reason to suspect that there's some kind of fermion.
Yeah. So that's it. That we talk about this tomorrow. So we try. We don't suspect because it's very hard, right? So it turns out that if you take the Heisenberg-Kitaev model, or you take the Heisenberg-Kitaev model, then the best way to do Monte Carlo is through this Fermion representation. in terms of the sign problem. That's what comes out of our results. So I don't know if this answers your question, but it may be, it's pure spin model. So we do pure spin model, and we go to Fermion. Seems to be a very contrived way of doing spins, right? When you think about it. But when you have a sign problem, it turns out to be the best way I know. I'll talk about this tomorrow.
So let's say I love magnetic order, I like breaking time, what's the next best kind of symmetry that might save us from having the sign problem?
Well, normally you don't. So we like magnetic order also, but normally we like magnetic order when it's spontaneously generated. So your Hamiltonian never breaks the time reversal, right? So that's because we're interested in fluctuations, right? We do correlations, we're interested in fluctuations. So we never really. You see, breaking time reversal symmetry is the same thing as doping a Hubbard model, right? So if I start with an attractive Hubbard model, half filling, and I can do my Monte Carlo, and I put in a magnetic field, right? Then I can do a canonical transformation, which maps my magnetic field to a chemical potential in the repulsive Hubbard. So if you break time reversal symmetry sometimes, then you really run into a sign problem. There's nothing. I hope I answered the question. So if you there's a very interesting paper of Enesberg which asks us the question. Okay, here's the thing. We have symmetries, and we're protecting all our calculations from symmetries. What are the possible states we can get in an RG sense if we just respect those symmetries? That's an interesting question. And so it turns out that we can do a lot of things. One thing which we cannot do in a translationally invariant system is local moments in a metal. That's a doped Hubbard, or that is extremely hard. What I'll show you tomorrow, thank you for the question. Very good. What I'll show you tomorrow is that if you forget about translation symmetry a bit, then you can do that. That's it.
Is there any more questions? One last question.
So the FL star
Yeah.
that we found here, is it the same thing that one finds in the pseudogap?
Oh, I was not aware that the FL star was a pseudogap. Right? Is there a deconfined? Oh. I don't know that. I just don't know that. But we can talk. We can talk about that. I don't know that. The best FL star we will show tomorrow is basically a spin chain, right, which is decoupled from an electron gas. That's the best FL star I can do.
Okay, let's thank the speaker again. We now have the coffee break. We will resume at 11:20. Sorry, did I go too past?
No, of course not. Of course not. Of course not. Of course not. No. I can cope with that. No, it's very nice that I have. The mic is still. So I have too many.